Welcome to Module 10. We've looked quite a bit at finding derivatives of different types of functions and using them to describe function behavior. Now we shift gears to consider antiderivatives. Let's begin with an analogy involving data compression. Compressing data allows us to save space on storage devices and speed up file transfers. The zip compression format was developed in 1989 by programmer Phil Katz. When we zip a folder, we compress the data and reduce it to a smaller single file. This compressed file still contains all of the original data information, but in a form that takes up less space. Suppose we think of the original data as if it were some type of function. When we zip the data, we are changing it into something else. Think of zipping the data as the differentiation process, and the reduced compressed file as the derivative. All information about the original function is contained in the derivative. And just like we can unzip a file to restore the original data, we can reverse the derivative process to find the original function. This process is known as antidifferentiation. Let's consider an easy example. Suppose that we know that the derivative of a function is f prime of x equals 2x, and we would like to know what the original function was. After giving it some thought, you can probably guess that the original function is f of x equals x squared. It's easy to check that the derivative of x squared is 2x. So, x squared is an antiderivative of the function 2x. Note here that I am saying an antiderivative. This is because there is actually more than one. For example, f of x equals x squared plus 5 also has a derivative of 2x. So does f of x equals x squared minus 1. In fact, any function in the form f of x equals x squared plus c, where c is a constant, would be an antiderivative. So when we reverse the process of the derivative, we generally get answers in the form some function plus c. When we include the plus c, we refer to this as a general antiderivative. Let's look at an example. Let g prime of x equal 3x squared. We want to find the general antiderivative of g prime of x. The general antiderivative is the function g of x, and by observation, we can see that if we took the derivative of x cubed, we would get 3x squared. So the general antiderivative is g of x equals x cubed plus c. Notice that g prime of x is equal to 3x squared no matter what the value of c is. Now, when we write the integral of 3x squared dx, this means that we want to find the general antiderivative of 3x squared. Here, the elongated s is called the indefinite integral. The dx at the end of the notation tells us which variable we are interested in. So let's look at an example. We want to find the indefinite integral of 2x dx. Now this notation tells us that we want to find the general antiderivative of the function 2x. As noted before, we know that the general antiderivative is x squared plus c. Now, the rest of this lesson will concentrate on various rules for finding indefinite integrals, or general antiderivatives if you prefer. However, let's take a moment to consider why we might want to find an antiderivative in the first place. There are many occasions on which we are given data that represents rates of change. For instance, we might monitor the rate of traffic over time in a network. We might analyze the rate of user interactions with an application. We might track the rate of energy consumption in an operations center. We might analyze the rate of bandwidth usage in a streaming service. In each of these cases, the indefinite integral provides a bridge from a known rate of change to the original quantity of interest. Let's move on to some of the most common integration rules. The constant rule tells us that when we integrate a constant k, we just get k times x, or whatever variable we're dealing with, plus c. In the power rule, when we integrate x to the nth power, we're going to add 1 to the exponent to get x to the n plus 1, and we get that n plus 1 also in the denominator. In the linearization rule, If we're integrating something in the form a times f of x plus b times g of x, then we're going to treat this the same way we do with derivatives. We'll just bring the a and the b along for the ride, and we will take the integral of the f of x and the integral of the g of x. The sine rule tells us that the integral of sine of x is equal to negative cosine of x. And the cosine rule tells us that the integral of cosine of x is equal to sine of x. Now remember that these rules are about general antiderivatives, so don't forget to add the plus c in each case. Consider some more examples. So in this example, I'm trying to integrate the function 4x cubed plus 5 with respect to x. I'm going to start off here with the linearization rule, which tells me that I can split this up into two integrals, and I've got a constant right here I'm going to bring out in front of this first one. So I'm going to rewrite this as 4 times the integral of x cubed, and I'm integrating that with respect to x. And then I've got the integral of 5 with respect to x. I've got this 4 out here in front, and when I take the integral of x cubed, now I'm using the power rule, which tells me to add 1 to the exponent, and I get that same number downstairs. And I know I should be adding a plus c right here, but let's hold off on that for just a moment. Let's address this one over here. I'm taking the integral of just a constant, which is 5. And I know that when I integrate that, I'm going to get 5 times x. And so instead of adding a plus c onto each one of these things, I'm just going to combine those into 1 plus c out here. Now I see I can do a little bit of simplification. I've got a 4 times x to the 4th over 4. So I can rewrite that as just x to the 4th plus 5 times x plus c, and that's my indefinite integral, or if I want to call it the general antiderivative, that's what I've got. In the previous example, we found the general antiderivative to be f of x equals x to the 4th plus 5x plus c. Suppose that we had a bit of extra information about this function. This might be in the form of a given point on the graph of f of x. For example, suppose that we knew that the graph passed through the point 1, 5. Then we would have enough information to determine the value of c. When we have an expression where c is known, we call it a specific antiderivative. Alright, so in this problem, we are told that f prime of x is equal to 4x cubed plus 5, and we want to find the specific antiderivative f of x given that f of x passes through the point 1, 5. Well, we know that f of x is going to be the antiderivative of f prime of x. And we know that that means that we have the integral here of 4x cubed plus 5 with respect to x. And this is the problem we did in the last example. We know that this turned out to be x to the 4th plus 5x plus c. And so we know that f of x is equal to x to the 4th plus 5x plus c. Now, if we knew what c was, then we would have our specific antiderivative. But we're going to be able to find c because we have some extra information here. We know that f of x passes through the point 1, 5. And that implies that the function is equal to 5 when x is equal to 1. So let's go ahead and plug in 5 in place of f of x, and we'll plug in 1 in place of x, so that means we'll have here 1 to the 4th plus 5 times 1 plus c. Okay, so it looks like that means that 5 is equal to 1 plus 5, so that's going to give us 6 plus c. And from there, I think you can see that c will be equal to negative 1. So I just found out the value of c. And that implies that the specific antiderivative for this function is f of x equals x to the 4th plus 5x plus c, but since I know that c is equal to negative 1, I'll go ahead and put that in. Let's analyze this example slightly more. We started with the fact that the derivative is f prime of x equals 4x cubed plus 5. This means that we know, for any value of x, the slope of the line tangent to f of x. For example, when x equals 0, we know that the tangent line has a slope of 5. Let's sketch the slopes for several values of x in what's called a direction field. Now we have to use our imagination some, but we might be able to visualize a function that could be drawn that would fit the various slopes just by looking at it. Luckily, we know a function that fits. It's the antiderivative. Now the general antiderivative includes the constant c, and changing the value of c shifts the graph up or down. But note how the graph still aligns to the drawn slopes. In the previous example, we knew that the graph of f of x passed through the point 1, 5. Now there is only one antiderivative whose graph passes through the point 1, 5. This is the antiderivative corresponding to c equals -1. So the specific antiderivative is f of x equals x to the fourth plus 5x minus 1. Let's consider another example. After implementing a new AI assistance system, the function f prime of x equals 2x plus x squared plus 8 sine of x measures the weekly improvement in seconds in average response time for tech support tickets. Here, x is the number of weeks since the system was introduced. Initially, there was no time saved at the beginning of the implementation, so f of 0 equals 0. We want to determine f of x, which represents the total improvement in response times. So in this problem, we're given the derivative, f prime of x equals 2x plus x squared plus 8 sine of x. So we know that f of x will be the antiderivative of that, or the integral of it. Well, let's go through and see if we can find the antiderivative. I think we could probably do this first part right here pretty easily. The antiderivative of 2x is just x squared. It's easy to check that the derivative of x squared is 2x, so that's a pretty straightforward one. We have x squared, so we're going to use the power rule here, which tells us to add 1 to the exponent, and then we get that same number in the denominator. So it looks like we get x cubed over 3. Now I'm going to go ahead and write down this 8 right here, and think about the antiderivative of sine of x. Now looking back at our formulas, we see that the integral of sine of x is negative cosine of x. And let's not forget to put our plus c at the very end here. Okay, so maybe we can clean that up a little bit. F of x is equal to x squared plus, I'm going to write this as 1/3 x cubed. I've got a minus 8 cosine of x plus c. So I've got the general antiderivative here. But what I want is the specific antiderivative. So I'm going to use this extra information that I have. I know that f of 0 is equal to 0. And that tells me that whenever I put a 0 in place of x, I get a 0 for f of x. So it looks like that gives me 0 equals 0 squared plus 1/3 times 0 cubed minus 8 times cosine of 0 plus c. Okay, so I know that 0 is equal to, let's see, this is 0 and this is 0. I have negative 8 times cosine of 0. I can see from my calculator that cosine of 0 is equal to 1. So that means I've just got negative 8 times 1 plus c. And straight from there, we can see that c is equal to 8. It looks like I have alpha of x is equal to x squared plus 1/3 x cubed minus 8 times cosine of x plus c, which I know is 8. And there's my specific antiderivative. And this function, f of x, represents the total improvement in response times. Consider another example. A software development company introduces a new algorithm to optimize data processing speeds. The rate of improvement, measured in milliseconds saved per operation, is modeled by g prime of t equals 4 times the square root of t plus 2 over t squared. Here, t is time in months since implementation. Given that after the first month of implementation, the algorithm saved a total of 5 milliseconds per operation, we want to find g of t, the total time saved in data processing operations. So in this problem, I'm given g prime of t equals 4 times the square root of t plus 2 over t squared. The first thing I'm going to do is just rewrite that. I'm going to write that as g prime of t equals 4 times t to the 1/2 plus 2 times t to the negative 2. And I'm just doing that so that I can use my antidifferentiation rules. Well, now we know that g of t is the antiderivative, or indefinite integral, of g prime of t. So we know that we have here the integral of 4 times t to the 1/2 plus 2 times t to the negative 2 with respect to t. Well, let's see, that will be, I'm going to write down this 4 right here because it's just a constant. I need to add 1 to the exponent, so I get t to the 3/2 over 3/2. All right, and for this one I get 2. I add 1 to the exponent, so negative 2 plus 1 would give me a t to the negative 1 over negative 1. I'll go ahead and put on my plus c here. And so let's go in here and simplify this a little bit. If I multiply the top and bottom of this fraction here by 2, then the 2 in the denominator will cancel with this one. That would give me a 2 in the numerator, which I can multiply by that 4. And it looks like that would just give me an 8 in the numerator, and I would have a 3 in the denominator, and I have t to the 3/2. Now over here, I've got a negative, so I'm going to go ahead and just make that negative 2 t to the negative 1 and plus c. So we've just cleaned that up just a little bit. And so I know right now that my general antiderivative is in the form 8/3 t to the 3/2 minus 2t to the negative 1 plus c. And so I need to figure out what c is so that I can get a specific antiderivative. Now, if we look back at the problem, we see that after the first month of implementation, the algorithm saved a total of 5 milliseconds per operation. In other words, when t equals 1, the function is equal to 5. So we know that g of 1 equals 5. And we use this information to find c. So I know that g of t equals 5 when I put 1 in place of t. And it looks like that's telling me that 5 is equal to 8/3 minus 2 plus c. And if we go in here and solve this thing for c, then what we find is that c is equal to 13 over 3. So it looks like we can write down our specific antiderivative. We get g of t equals 8/3 t to the 3/2 minus 2t to the negative 1 plus 13 over 3. This wraps up our first lesson into the world of integration. Here, we've looked at finding antiderivatives, also known as indefinite integrals. In the next module, we'll learn how to apply the tools and concepts learned here to solve an entirely new type of problem.